Unit 2 on energetics. And believe me, as I was writing this last night, I was like, oh my. Especially this is the definition side. Oh my. Formulas, equations, definitions, explanations. Yes, that's exactly what I said last night. I was like, oh my. Unit 2 review. Energetics. What do we mean by that? Yep.
What was it called? Energetic?
Energy and entropy, sure, and free energy, if you want to go through all the different things. Energy, entropy, free energy. Free energy being Gibbs for a reaction. So this is unit 2. We're first going to go over the formula. So if you want to get a ruler, feel free to pick up a ruler from the front of the classroom.
It's adjacent to the student resource station sign, which is above the trash can, not indicating that the trash can is our student resources.
How do we fix that?
That's hilarious. I love that that stayed like that, Yemi. You should keep that like that. It's really funny.
I gotta think about that for next year. This year it's too late.
Yeah.
The student resource station
Is the trash can. That's all you can. Figure it out. Oh my god.
That was a good part of yesterday. All right, here we go. Formulas to start. Formulas. The first one that I had is the delta S formula. Delta S reaction. You get this from taking the addition of the delta of the entropies of your products and subtract the entropies of your reactants. So it's products minus reactants, but the official formula is the summation of the S of your products minus the summation of the S of your reactants. And that's the entropy for a chemical reaction. Enthalpy for a chemical reaction is the exact same thing. Delta H reaction equals the summation of the H's of your products minus the summation of the H's of your reactants. That's our second formula. And our third formula is Gibbs free energy, which is delta G equals, you saw this in the bell work, delta H minus T delta S. Gibbs free energy. What is the one thing you've got to remember about Gibbs free energy? It showed up in the bell work today that you've got to be careful about.
Entropy is it's in kilojoules, but the entropy formula gets it in joules.
Right. So joules must be transferred to kilojoules. That's something you should remember, that they pretty much always give you an Entropy values in joules, and you have to change them to kilojoules, or else you're going to get your answer way wrong. It's going to be something way off because the units don't match, right? That was formula number 3, is the delta G formula. Formula number 4. We also saw, I tried to encapsulate in the bell work as many of the formulas as I could. So this one is delta H F equals delta H1 plus delta H Lattice. And in order to solve that, you've got to know what is delta H1. And what was delta H1 again? Make a note. What is that? The addition of your atomizations, your ionization energies, and your electron affinities. So the delta H1 is the sum of atomization, ionization energies, and electron affinities. That's what delta H1 is. So like as summarized as possible. Formula 5. Delta H lact plus delta H sol is delta H hydration of your cation plus delta H hydration of your anion. Stefan, you didn't want to go to honor roll? Well, oh,
Yeah.
do you still want to go down for honor roll? Oh, okay. All right. Underneath that, let's just go ahead and sketch out that Born-Haber cycle, like just a rough sketch of the Born-Haber cycle while we're here. And what I did here was put energy reactants. Delta H1. This right here is energy. Energy of products. Delta H lattice. And the difference between these two is delta HM. That's a rough sketch of the Born-Haber cycle. You start with the energy of your reactant. Delta H1 up, 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 generally speaking, except for electron affinity. First one is negative, which we'll talk about in a little bit. Delta H lat, big down, like very exothermic. And then the difference between your reactants and products energy is your delta HF, which for formation of an ionic compound is exothermic. All right, so that's formulas. The next thing is equations. I'll pause. But what I mean by that is chemical equations. What equations could you be responsible to need to write? Starting with thermal decomposition. Which is an AS chemistry standard which shows back up in A level. For carbonates, it's XCO3. And do you remember what the products are? For carbonates, thermal decomp.
XO.
XO
Then
and
That's just
CO2. Thermal decomp. The next one is nitrates. XNO3, 2, triangle, XO plus NO2 plus O2, and we did have to balance this one. It will be 2 here and a 1/2 here to balance. Thermal decompositions. Don't worry, we'll get to the trends about them later on the other page. Now it's just equations. The next thing is you have to know all your equations for all components of the Born-Haber cycle. Like you saw in the bell work today, there was one that was asked for atomization, and there was one that was asked for enthalpy of formation. You do need to know all your equations. So first of all, let's start with atomization. What is atomization?
Right.
It's actually standard state.
Yeah.
Right? To gas atom. Because standard state could be solid, liquid, or gas. Like it's just whatever the element standard state is. So it's element standard state to gas atom. Can't really give a formula for it because it just depends on what you have, what the atomization is going to be. But it's single gas atom is really important that you note. So that's atomization. The next one that we had also saw in the bell work is enthalpy of formation. What's that? Elements in standard
State.
state go to compound. Whatever compound they're forming. 1 mole of compound. That's called enthalpy of formation.
Does it also have to be like 1 mole of gas atom or like it can be?
Yeah, that's why I said atom, 1 mole, because it's always 1. So 1 mole gas atom. It's always 1 in the front, always. So when you're balancing, you have to have 1 in front of the product. All right, the next one is ionization energy. So first ionization energy, can I abbreviate that with IE? Is that okay for everybody to abbreviate that as IE for space? IE. This one is a little bit easier to predict. It is whatever you have always has to start in the gas phase. It has to be in the gas phase, not standard state. And then it goes to X plus 1 gas phase as well. And then what else am I not, what am I missing right now? There's plus E minus because you're ripping the electron off basically. So plus E minus. For all of these energy changes, you should know their delta H. Is the delta H positive or negative for ionization energy?
Positive?
Yep. Delta H equals positive, and you should write that. Just to, because all the energy changes, you need to know their delta H's. Enthalpy of formation could be positive or negative. For ionic compound formation, it is negative. But atomization is actually always a specific sign as well. What sign of delta H is atomization while we're at it? Is atomization positive or negative? Does it require energy to turn to a gas or release energy to turn to a gas? What do you think?
Positive.
Positive. It always requires energy to turn into a gas. Because you're going like from solid to liquid to gas, that requires energy. Or you're breaking a bond, that requires energy. Atomization is always positive. You should also, for yourself, put down the second ionization energy equation. What would that be? Second ionization energy. What would you start with? Just to get the pattern. X plus 1. So X plus 1 gas goes to X plus 2 gas plus E minus. And would delta H be positive or negative? To rip the second electron off. Positive. And would it be more positive or less positive than the first ionization energy? More positive, right? Why more positive? Because as you are ripping additional electrons off, your nucleus has a stronger hold on the electrons that are left. So your ion has a positive charge. It's more difficult to pull additional electrons off. This is called successive ionization energies. Also a topic in AS chemistry, but could definitely show up. Electron affinity. First electron affinity equation. So I'm going to summarize that as EA. What would that look like? We would start with whatever we have as a gas, but instead of taking away an electron, we add an electron. So it would be plus E minus goes to X minus 1 gas. Positive or negative? Delta H. Delta H here is always negative. It releases energy to add an electron. If it's a nonmetal that wants an electron. Second EA. We would now start with X minus 1. And we would go end with X minus 2. Delta H, positive or negative. This was actually something that was brought up in the class that I taught this. The first electron affinity, you always release energy. But once you have a negative ion and you try to add a negative charge to a negative ion, that's actually unfavorable, generally speaking, because negatives repel each other. So that means the delta H to make this specific process happen has to be Because if you remember, unfavorable is positive and favorable is always negative. So this is positive. And could there be questions where they just ask you what's the sign of delta H in these processes and you do check mark boxes? Absolutely. That's why it's important to review that. All right, so that's what ionization energies, electron affinities. The next one, lattice energy. What is the lattice energy equation? Which we call delta H lat. That's X plus whatever, plus 1, plus 2, plus 3. It depends on what the ionic compound is, right? X positive gas plus Y negative gas goes to what? XY, state of matter to form the ionic compound. What would the ionic compound state of matter be in? Solid at the end. And this is always 1 mole. Once again, all of these are 1 mole of the compound. And so should that be positive or negative? Positive or negative? Very negative. And so I would put here very exothermic because it releases a lot of energy to go from gas ions that have high energy to an ionic solid that has very low energy. That's why even though the electron affinity process is unfavorable, the overall process is very favorable to form an ionic compound. There's more. I'm not switching the slide yet. There's more to this side. Enthalpy of hydration and enthalpy of solution we still have to do. These are all the factors in the Born-Haber process. So all of these right here are the Born-Haber process equations. That's a lot for just one thing. The next set is going to talk about your enthalpy of hydration and your enthalpy of solution. So enthalpy of hydration equation. This is where you take your gaseous ion and you dissolve it in water. So you have a different equation for your cation. You should write this. And then you have a different equation for your anion. And this is basically just saying we are dissolving this ion in water and we utilize the gas phase so that we can use the lattice enthalpy factor as part of the equation. So it helps us put together the enthalpy of solution equation. So this is enthalpy of hydration. Remember there's two, one for the cation and one for the anion. You hydrate the cation and you hydrate the anion. It both releases a lot of energy in that process. So both of these are actually negative. Delta H hydrations are always negative. So always exothermic. Always negative.
And so it always goes from gas to aqueous.
Yep. Gas ion to aqueous solution. Aqueous gas. Aqueous ion. That's delta H hydration. Delta H solution is taking an ionic compound and dissolving it in water, like taking salt and dissolving it in water. So it's XY solid plus AQ goes to XY AQ. This is used to predict solubility, like we saw in the bell work. If negative or only slightly positive, it's soluble. If it's more positive, the increase in positive means decrease in solubility. So the more positive the value is, the less soluble your salt will be. Because oftentimes you have to track trends. Is this one more soluble or is that one more soluble? The more positive, the less soluble for the H solution. And you know, we can't leave this side without talking about the actual energy cycle. You remember energy cycles? You know, with the arrows that go like that? Let's do the energy cycle. For solution. This is where you have the arrows that go like this and like that. Remember that? Ring a bell? This side is gas ions. This is ionic solid. And down here is ions in aqueous solution. And then above each of these arrows, we put each of the energy processes to go from gas ions to ionic solid. This is the enthalpy, lattice enthalpy, delta H lat. This right here to go from the solid to AQ, the ionic solid to the aqueous solution, that's delta H sol. And then gas ions to ions in aqueous solution, that's delta H hydration. And so this is the enthalpy cycle that gives us the equation, the equation right here. This enthalpy cycle gives us equation number 5. In case they ask you to write the cycle, that would be it. Sometimes you're asked to write the cycle. In the bell work you weren't, you were just asked to know how to calculate. That is this energy cycle that gets you this equation, actually. Because if you add this, it's delta H lattice plus delta H sol for one side, delta H hydration on the other. And you just have to remember there's always 2 hydrations, one for the cation and one for the anion. That's why I write it twice when I write it. And that was part 1 of the review. I'll pause till you all let me know I'm good to move on to part 2. But I will warn you, this was part 1. This is part 2. Part 2 has a lot of words. I'm sorry. If you want to try to pare down words as much as possible, please feel free. I tried to write as few words as possible, but with the definitions, sometimes you have to like include a lot. There's so many enthalpy definitions.
I think that's senior has the tougher explanation.
It has the toughest explanation. I have them here. The one for the solubility of hydroxides in sulfate. I think that is the hardest one. I was thinking last night, like, how to possibly remember it. I came up with something. You'll see if it sticks. We'll see if it sticks. Diane had one last year, and I don't remember what it was. It didn't stick. Okay, so are we good to move to the back, or do you still need some more time here? Are we good? Okay. Definitions. The next column is definitions. These are the word for word. Cambridge can ask you, define blah, blah, blah. So basically I went through your standards paper that I printed out for you, and I literally went through and check marked each one as I went along to look for the official, Cambridge definitions. And so here we go. Starting with enthalpy of ionization. Are you good with me like writing delta H instead of enthalpy? Like, can we cut that down a little bit? All right. So the first one is delta H, atomization, the definition. So enthalpy of atomization. What is the definition? This is the energy change when 1 mole, it's always 1 mole, of gas atoms are formed from elements in standard conditions, basically standard state. And if you know your equations, you're basically just saying the equation, if you think about it. Like when you're saying the definition for enthalpy, you're literally stating the equation in words. You're saying I'm making 1 mole of gas atoms from elements under standard conditions. Under standard conditions is the same thing as standard state. But I'm going to use standard conditions because that's what Cambridge officially uses. So standard conditions. That's the first one, delta H atomization. The second one, and I went through them in order. The second one is delta H lattice. So this is lattice energy. If they ask you to define lattice energy. Energy change when 1 mole of an ionic compound forms from gaseous ions. Energy change when, once again, and you can detect patterns here. You all are very good at detecting patterns. It's always 1 mole. And then you're looking at what actually happens. When 1 mole of an ionic compound
Forms
forms from gas atoms. Or second. Ageless.
No.
The next one that they asked us to explain is first electron affinity. And I thought it was interesting they said just first electron affinity. Like in the standard it says first electron affinity. So first,
Yes. Isn't the lattice energy gas ions and not gas atoms?
you're right. I don't know if I wrote that or if I, yeah, I framed it. It's gas ions. First, electron affinity, which I'm going to write delta HEA. This is the energy change, always the same thing. When 1 mole of electrons is added to 1 mole of gas atoms. And they say to form 1 mole of gas ions. 1 mole of gas ions. 1 mole of electrons, 1 mole of gas atoms to make 1 mole of gas ions. So basically, you're literally just stating the equations is all you're doing with all these definitions. In my opinion, if you can remember the equation, you just have to state it in words for the definition. Enthalpy hydration is the next one. Delta H, hydration. Enthalpy change, and so energy change. When 1 mole of gas ions dissolves, and this one does have a little bit something different, in sufficient water. To form a dilute solution. Dilute solution. H hydration. Delta H solution. I feel like every year they the Cambridge examiners take a dart and they're like, this random one this year, this random one that year. So it's like, this is your bank of, they're going to pick these terms and you're going to get one of them.
They just have chemistry themed dice in there.
Roll the dice. This time we're going to talk about this. And delta H though. This one has a little bit something different because of the fact that energy can be absorbed or released. You have to state for delta H though because it does have an effect on solubility. So for delta H though, it's the energy absorbed or released. Absorbed or released. When 1 mole of an ionic solid dissolves in sufficient water again, that sufficient water to form dilute solution. There's one more definition that I guess I'll just write at the very top on the next, like next door if you've got space underneath. The last definition, like straight up definition for this unit, is entropy. The last definition is entropy. And so entropy is, and you've got to be careful with this because a lot of you on one of your quarterlies or tests said the first part right, but you forgot the second part. It's the number of arrangements of particles. The number of arrangements of particles and their energy in a system. That's what entropy is defined as. And that's the definition part of this unit. Straight up definition.
Wait, so you don't need to know the ionization energy one?
That's from AS chemistry. But doesn't hurt to know it. There's a non-zero chance it could show up, but I'm out of space. So you can add it in if you want. Ionization energy definition. Because that was a AS chemistry standard to define that, but there is a non-zero chance that shows up, sure. So the rest of this is common explanations and trends. And there are so many. And my opinion is that some of the hardest, most difficult to explain topics are in this unit. Specifically, the solubility of sulfates and hydroxides, I think is a pretty difficult concept to explain, but let's get through it. So, and I went through once again the syllabus to check all the different things they wanted us to compare. The first one is, what are the factors that affect electron affinity? So what affects electron affinity? So the idea is for electron affinity, what we're talking about is adding a mole of electrons to the nucleus, right? So the first electron affinity, I'm going to write it here, first EA depends on the attraction between the electron we're adding and the nucleus of whatever atom we have. And so the concept that you need to grasp, and this is a concept that if you grasp this, you can use this for other explanations as well, is the stronger the attraction between the nucleus and the electron, the more energy is released. So stronger attraction is favorable. So more energy released which is more exothermic. So more negative is the idea. Specifically, if I'm comparing two atoms on the periodic table, if there is an increase in the nuclear charge, what was the nuclear charge again? There's an increase in the nuclear charge. What's the nuclear charge? How positive the nucleus is, right? So if there's an increase in the nuclear charge, there's an increase in attraction. And if there is a decrease in size, the smaller the size, the greater the attraction, because the closer the electrons are to the nucleus. So smaller size atoms will be more attracted to electrons. So smaller size, greater attraction. So this allows you to compare across periods and to compare down groups. Across a period, what's the factor? Nuclear charge. Down a group, what's the factor? Size. You need to write that down in your head. Nuclear charge is always across the period, because as we go across the period, we're not significantly changing the size, but we're significantly changing the amount of protons we're adding to the nucleus. And that's why across the period is always nuclear charge. Yes.
You mentioned shielding.
You don't have. I don't know that I've ever seen shielding on a paper. Ooh, I guess there's a non-zero chance. Could be the year. Could be the year. But I don't think I've ever, like, you can look up all the paper 4 mark schemes you want. I've looked at about probably 70. I don't think I've seen it. But this is definitely what you want to discuss. All right, so then that is for first electron affinity. What about second electron affinity? What was the explanation of why it's positive? Second EA, always positive. Why? Due to why? Why is the second electron affinity positive every time? Go ahead, Issa.
Because the opposite is on the electron and the negative
Due
electron.
to repulsion between electron and negative ion. The negative ion you formed after the first electron affinity. That's the concept. That was our first set of understandings, was the electron affinity explanations that they want us to understand. The next one is lattice energy factors. And I'm going to do this with arrows because I think arrows is the easiest way. And then you just write bigger or smaller when you're explaining. So the larger size your ion is, the smaller the lattice enthalpy. Meaning, the larger the size, the less energy is going to be released. Conversely, if I have a very small sized ion, it's going to release a lot more energy because, again, smaller size means greater attraction. Smaller size, greater attraction, greater energy released. So greater size ion is smaller lattice enthalpy. Smaller size ion, they're inversely proportional, is greater negative lattice enthalpy. Enthalpy and energy, remember, are used synonymously as synonyms. And what about the greater the charge? What if I have a greater positive or negative charge on my ion? What would that do to the lattice enthalpy? The higher the size of the charge, like +2 versus +1. The greater the attraction, which means the greater the energy released. Remember, greater attraction is always greater energy released. So greater negative lattice enthalpy or energy. The next category, factors that affect enthalpy of hydration. Do I have space here? I have barely any space. Delta H hydration. Factors.
Yes.
Yes.
Why is it smaller like max?
Smaller minus means closer to 0.
Oh, okay.
Like instead of -1,000, it's -200. Smaller negative means closer to 0. Like less energy released. That's why it is a smaller negative. Delta H hydration factors are actually the same as the lattice energy factors, the same as the electron affinity factors. So the smaller the ionic size, the greater the energy released. Which means greater negative. And the greater the charge, the greater the delta H hydration. So you should see a pattern. The greater the size, the less energy is released. The smaller the size, the more energy is released. The greater the charge, the more energy is released in all of these scenarios. Electron affinity, lattice enthalpy, and delta H hydration. It's the same factors. Just you can use it to explain all of them. And then we're to the big stuff, the trends. No. The trends. Trend in thermal stability. Down group 2. For nitrates and carbonates. Put like a little box around these when I was doing it last night. These are the common explanations. So thermostability means as we go down group 2, how easy or how difficult is it to decompose, to thermally decompose. And I'm going to put bullet points, and you can put bullet points like on a Cambridge exam, you're allowed. So 1 mark might be thermal stability increases down group 2. Down the group. The second point is the ionic radius of your cation increases. Which means it has, you remember the words less polarizing power? So there's less ion polarization of the anion. The anion being either the nitrate or the carbonate, meaning it is harder to decompose as you go down the group. And so this is a standard 2 or 3 mark explanation question. You know it or you don't. Very common. So the next one is variation in solubility of sulfates. Trends in solubility of sulfates down group 2. Put a box around it. This is the one that can be 4 points, if you'll recall. Like this one and hydroxides are both 4 points. Getting closer. All right, sulfates. Solubility decreases down to 2. That's one possible point. The next point that's the same in both explanations is both, remember the solubility relies on 2 factors, the lattice enthalpy and the hydration enthalpy. We have the equation for that. So the delta H lat and the delta H hydration both become less exothermic. Why do they both become less exothermic? Because what I said here, as we go down the group, the size of the ions get larger, and if the size of the ions get larger, we have both a smaller lattice enthalpy and we have a smaller delta H of hydration. Like it's the same factors for both. Here they are. Oh, it's just you. Welcome back.
Get to get out of my seat now.
What if I
I
don't?
think Daniel has taken your seat. Now what you have to remember is for this one, the delta H hydration changes more. which means that the delta H sol becomes less exothermic. Yes.
Do we have to explain why?
Nope.
So we don't have to make reference to the size of the.
Nope. Not for this explanation. If they ask this, yes. If they ask why the delta H hydration, as we go down the group, includes like the delta BF hydration as we go down the group. If we ask why is this energy released, then you have to explain why.
No, I mean, do we have to explain why?
This is literally the marks.
Organization changes more than.
Nope. Just one changes more or the other one changes more. That's literally all you gotta say. This is literally the least amount of words to say to get the 4 marks on this question. So I thought about it last night. I was trying to figure out like what would be a way that we could like memorize this. Remember that the solubility decreases for sulfates and it increases for hydroxides. Those 2 factors, that's the opposite. And one, the delta H hydration changes more, and the other one, the delta H lattice changes more. So I thought, okay, so what if I just said sulfate is sulfide? Sulfide. And I was like, sulfide, that's a thing. And so I was like, maybe that will be a way to remember that the hydration enthalpy changes more. Like try to like put acronyms and stuff to help you remember. Because otherwise it's hard to remember which one changes more. It's a lot of thought processing. You don't have a lot of time for that 100 marks. So yeah, sulfide. Sulf, the hydration changes more. That's what I would remember. Yes.
Was it like hydroxylate? No.
Hydroxylat.
Yeah.
Hydroxylat. I don't know. If you can like workshop something better, let me know. But sulfide actually sounded like a word that is sulfide, right? It's like that one makes sense. Hydroxylat. But something that helps you because it's a 4-mark question. And if you get part of it wrong, you get a contradiction, which may mean the whole thing's wrong. So you want to make sure you try to net those 4 marks because they're easy 4 marks if you can remember which one changes more. Yes.
Or you could just like reverse engineer it if you remember that sulfides are like the.
You could try to reverse engineer, yes. All right. So then what is the trend in solubility of hydroxides? Let's write it down so we have it, right? Trend. At the end, just like last time, my computer started giving up. It's okay. It just needs to make it a little while longer. It's like taking like
all that
6
down.
lessons and putting it in one paper.
I'm not reading
Go ahead.
down. Let's take some.
Down.
Daniel, give me yours, and then
Two.
we'll trade.
You
Daniel,
can come on in and join
you trade,
in.
right?
Don't worry, miss, we made it back in time.
Uh-huh. Trend in solubility of hydroxides down group 2. So remember that the sulfates and the hydroxides are opposite. So if the sulfates decrease solubility down group 2, the hydroxides increase solubility. So this is solubility increases down the group. Down group 2. This statement is the same. Delta H lattice and delta H hydration both become less exothermic. Delta H lattice. Told you my computer's been. And delta H hydration both become, hold on, I'll get the door, less exothermic. But this time, what changes more? Welcome back. The delta H lattice changes more. And the last statement is this means the delta H solution becomes, instead of less exothermic, it becomes more favorable, so it becomes more exothermic. So delta H sol becomes more exothermic. For those of you who just came in, you may want to take a picture because this is what you're gonna have to get onto your one pager. Do we have space for more? Because I actually have a little bit more on this paper. I just have to use a third slide. I'll pause for a little bit for those of us who are still writing. Give like 2 minutes and then we'll continue.
And then some both may both become less exothermic.
Both factors become less exothermic, but one changes more than the other, which changes the equation. Like whether delta H still becomes more or less exothermic at the end. So both factors become less exothermic, but one changes more than the other. Is the idea. And as I said, I would do sulfate with high, sulfide changes more, and then hydroxide with lat. I don't know, workshop that. Get back to me if you come up with a good acronym. But this is what you have to say for the 4 marks, exactly that. And that's 4 marks. That's a, you know, you could have some very hefty math buffer question for the same 4 marks. All right, ready for more? We still haven't went over entropy. That was just the chapter 19 stuff. But thankfully, the chapter 23 is a lot less. Like most of the explanations are chapter 19. Picture?
Just trying to sound really excited. No, but like that's like I need to make sheet change to that.
Oh.
That one.
Here. Picture? I have a little bit more. I'm gonna write the next one on Sunday before your class on Monday. How long can electrochemistry be? The one where you have to write the buckets?
No. Like that's the most interesting one for me, but like it's the most confusing too.
The positive negative on this one is actually positive.
Wait, 3 pages? I remember how we kept calling them buckets instead of
Yeah.
Yeah.
If they're the beakers, the anode and the cathode.
buckets.
Don't write buckets on a Cambridge exam.
Should we lose marks if you put buckets on the
I'm
camera?
pretty sure. They're gonna be like, what's a bucket? Okay, so last topic. Entropy and Gibbs free energy. So change in entropy. Remember that entropy is how much disorder a system has. And so what you have to remember is that if entropy increases, delta S is what sign? If entropy increases in your system, what is the sign of delta S? You should know this, positive. And if entropy decreases, what is the sign? Delta S is negative. Okay? What about delta G, the signs of delta G? If delta G is positive, what does that tell us? Reaction is not spontaneous, meaning it does not happen. So if your delta G is positive, the reaction currently will not happen. Your reactants will not turn into products. If delta G is negative, what does that mean? The reaction is spontaneous. What about the factors that affect feasibility of reaction, right? So factors that affect feasibility, which is whether it's spontaneous or not. We actually use this equation to help us out. For delta H, what is favorable, positive or negative? Negative, right? So remember, delta H positive is endothermic, which is not favorable. And delta H negative, exothermic, is favorable. So, if my delta H is negative and my delta S is positive, what will be my sign of delta G? If my delta H is negative and my delta S is positive. So negative means favorable, positive means favorable. Delta G will always be negative. Meaning no matter what temperature your reaction is at, the reaction will happen. It will happen. So far so good? What if we flipped it? What if delta H was positive and delta S was negative? Meaning this reaction is endothermic and it would result in less entropy. What would be the sign of delta G? If the signs are opposite and you have both unfavorable scenarios, then your delta G is always positive. And there's no temperature that you can change the reaction to make this reaction happen. So if the signs are different for your delta H and your delta S, the reaction's either always favorable or it's not favorable ever. So if the signs are the same, like if delta H was negative, which is favorable, and if delta S is negative, which is unfavorable, what's delta G? Either positive or negative dependent on temperature. So if the signs are the same, the idea is if the signs are the same, the delta G is positive or negative dependent on temp. And you might have to figure that out in a question. Like what temperature would make the delta G favorable, like for it to be a spontaneous reaction. So the same thing would be true if delta H was positive and delta S was positive. There will be a temperature range where this reaction can happen and a temperature range where this reaction cannot happen. The idea being the reaction is dependent on temperature. That is the end. For those of you who just came in from honor roll, I'll go back to the other slides for you to take a picture of it. But that's the end of the review. And the homework has been posted. Yes?